some thought into what the impact would be on using the unconventional fossil fuels. So here's the figure now where I've added the unconventional fossil fuels and the gigatons of carbon that are contained there. Notice how I had to change the scale. So the atmosphere, which we saw in the previous unit, was about 1,000 gigatons of carbon. Accessing and burning the unconventional fossil fuels like the methane hydrates would have an impact of over 250 times the carbon injected into the atmosphere. So I hope this stresses to you that it's a huge impact to take those resources and burn them. And regardless of whether or not you believe in the global warming impact for the numbers that we have right now, this would be a huge impact in changing the composition of the atmosphere. So, if you accessed all the non-traditional fossil fuels, you would release over 100 times the carbon loading into the environment compared to all the oil reserves, if you used all the oil reserves. So, we talked about at the beginning of this class, what are the drivers for changing the way we use energy? And we should change the way we currently use energy. Because if we continue on the path that we're on, we're going to have a pretty significant environmental and ecological impact. And it's very uncertain what that impact, what the cost of that impact will be. But we can generally guess they're not going to be good. There's also a lot of benefit associated with being highly efficient. So it appears that fossil fuel use will continue because essentially right now they're not scarce resources and we don't have cost-effective alternatives. So we look at the cost-effective equation. We say, okay, if something were less expensive, we would use it. And that's pretty well demonstrated behavior. What we saw in particular in the United States and in general around the world, the oil prices in 2008 and specifically the cost of gasoline spiked. And that caused a pretty dramatic shift in behaviors. People moved away from buying large SUVs and big gas-guzzling hogs, and they shifted to buying hybrids and also subcompact and small, very high efficiency, high mileage vehicles. So fossil fuel prices can increase, but we've seen scarcity isn't going to drive those prices up. And in general, we can see that oil prices actually follow some pretty well-behaved trends that are generally caused by pure economics. So increased demand causes increases cost. As we add more oil, let's say, to the market, then you drive the price down, et cetera, et cetera. So that type of behavior is pretty well explained. And we can expect that fossil fuel prices to increase unless we have specific legislated control, and we've seen that in some countries. And some examples include fuel taxes, carbon credits, cap and trade programs, et cetera, et cetera. So this is one mechanism by which we can drive people to use alternative fuels. Alternatively, we can drive down the cost of the energy carriers that are in competition with fossil fuels. And make no doubt about it, it's a competition. And right now, all the alternatives are losing the competition. They're much more expensive than the low costs of oil, natural gas, and coal. So let's compare those energy carriers. So what we have here is the energy density for different carriers. And this is a graph that I generated. And now I switched to kind of stationary power units, which are watt hours, which essentially are joules per kilogram. But this is kind of the way the electrical power community likes to use their units. So this is the specific energy. And what we see here is, again, this is a log scale. Let me anchor you. And what we see is hydrogen here at the top. And many of you have heard about the hydrogen economy, and we should have hydrogen fuel cells, et cetera, et cetera. And this is why. It's because hydrogen has the highest energy density of all these energy carriers. Okay. Now this is, I'm showing you a number that when I've pressurized hydrogen to 250 atmosphere, we can compare that to methane pressurized to 250 atmosphere, and you can see there's almost a factor of 2 or 3 higher energy density associated with hydrogen. And then we have gasoline, diesel fuel. This is N-heptane. This is isooctane. These are both surrogates. N-heptane is a chemical surrogate for diesel. Isooctane is a chemical surrogate for gasoline. JP8 is a jet fuel. Biodiesel, 100% biodiesel derived from plant matter, 100% biodiesel derived from animal matter. Ethanol, methanol, And these are your liquid fuels. And you see that the liquid fuels have very high energy densities. If we hop over to the right-hand side of this graph, we see the coal and oil that are used mostly in the stationary sector. And we can see this is subbituminous, and this is bituminous coal and oil distillate. And you can see that those are also very high energy density carriers. And we look down here, and we have to drop 2 decades down to even put these on the same scale. What we see are the current energy densities for battery technologies. Now, these are improving steadily every year. So these numbers creep up every year, in particular for lithium ion. But here you have zinc air, nickel metal hydride, nickel cadmium, and of course lead acid. And lead acid is still the primary or the largest number of batteries in the transportation sector, of course, for the lead acid batteries that are used for starting your engine. But you can see lithium ion has some pretty attractive features in comparison to these others in terms of the energy density. So hydrogen wins on an energy per mass basis. And we can see the challenges of trying to move pure electric vehicles, which require batteries for storage, into the transportation sector right here, right? We need to see a factor of 2 improvement at least. Ideally, we'd see an order of magnitude improvement in these fuels. But otherwise, we can see if we compare bio-derived fuels, and ethanol and methanol can be bio-derived. Methanol typically right now is derived from coal, one of those solid to liquid fuels. But ethanol is often derived from plant products. So we see that in the United States. Ethanol is derived from corn in Brazil, sugarcane, beet stock, things like that. But the liquid fuels all have about the same energy density, with the exception of compressed, these are the vapor phase fuels here, which have a slightly higher energy density. So you say to yourself, why aren't we running around on hydrogen right now? Why aren't we fueling all of our vehicles on hydrogen? It's got this great energy density characteristics. Well, that's this graph. So here's why we're not using hydrogen. It's one of the reasons we're not using hydrogen. If we go and we look at the energy density now on a volumetric basis, so now here I have my joules per liter or watt hours per liter basis. Now what happened to hydrogen? Oh my goodness, it fell off the chart, right? So on a per volume basis, even pressurized to 250 atmosphere, the hydrogen is just barely better than the battery technologies. But notice that the diesel or the liquid fuels remain at the top. So the liquid fuels have become the energy carriers for the transportation sector for very good reasons, because they have high volumetric and specific energy properties, and they're cheap. So within this sector, within this group of liquid fuels, the ones that rise to the top are diesel and gasoline and JP8, again, as the air transportation example, because these are the least expensive. The bio-derived fuels and even the bio-derived alcohols are still more expensive than the fossil fuel-derived alternatives. But if we can make processes, renewable processes in particular, that can reduce the price, these fuels have very attractive features for the transportation sector. Okay, let's keep going. Let's take that information and take the energy density here, now on a per volume basis as my y-axis, and on a per mass basis is my x-axis. And what we can see is that we want to be in this quadrant. We want to be in the northeast quadrant, because that gives me the best of everything. And I intentionally left these all clustered here so you can't see them, because again, this is why we've naturally in society selected these fuels for the transportation sector, because they meet both those criteria. And again, here's my hydrogen, which meets that lovely per mass criteria, but not so much the volumetric criteria. And of course, here's my battery technologies. Now, for fun, if you really wanted to do something creative, is you could take this plot and add uranium to the plot and see what the energy density is associated with the nuclear fuels. And again, you'll see everybody kind of crushed by the energy density associated with that fuel. So this gives you really just a discussion points for the transportation sector. Within the stationary sector, typically we don't care as much about the energy density because we're not carrying that fuel as far as we are with the transportation sector. But you can see again these drivers for what are the attractive thermodynamic properties of these fuels. Okay. So they have high energy densities, and we have a lot of fossil fuel resources. So we have scale. We have a lot of fossil fuels, and they provide a lot of attractive characteristics for us for both stationary and transportation sector. Why are we pursuing solar and geothermal? Or maybe I should rephrase that. Why aren't we pursuing them more? They're great resources. They're vast resources, but they're diffuse. And they require, I think I made this word up, densifying. Or maybe a better description would be to concentrate that energy. So let's consider solar energy. And these are extremes, and you can nitpick and you can say why we can't use those extremes, and you're exactly right. But let's at least look at the scale. The Earth intercepts a huge amount of solar radiation every year. The solar flux, which is also referred to as the solar constant, is about 1.4 kilowatts per meter squared outside the atmosphere. Now, we lose a chunk of that energy when the solar radiation is transmitted through the atmosphere. So we're going to lose a little bit of this solar flux. But for sake of this discussion, let's just use 1.4. So I take that solar constant and I say, well, I need the projected area. This gets into radiation heat transfer. And that projected area is pi times the radius of the Earth. And you do that calculation, what you see is that on an annual basis, the Earth intercepts 5.4 times 10 to the 24 joules per year. That's huge. The annual global demand for energy in all sectors is 4 orders of magnitude smaller than that. The solar energy that's intercepted by the Earth could more than meet the current global demand for energy. Now, here's my nitpicky. You'd skew all of the heat transfer for the world, right? You'd have a lot of issues with it. You would still have an impact if you tried to harness all of that energy, and it'd be an adverse impact on the environment and the ecology. But the point being is there's a lot of energy there. And go back to the very first unit and go look at how much energy is generated by renewable. And that's all renewable. That's solar, that's wind, that's hydro, that's geo, is less than 1% of the global energy use right now. So clearly, there's room for improvement. Okay, now let's consider geothermal. So geothermal reserves are also huge. So geothermal is based on the fact that if you go below the frost line, the temperature of the crust of the Earth, the surface of the Earth, is about 52 degrees Fahrenheit. If you keep going deeper, the temperature increases. So if you take, this is an estimate out of a report out of the Massachusetts Institute of Technology, MIT in the United States, and they did a really extensive report on what are the recoverable resources for geothermal energy. And they estimated over 13 million exajoules, or over 13 million times 10 to the 18 joules of thermal energy are available through what they refer to as enhanced geothermal systems. And that's essentially pretty deep mining in order for you to extract that thermal energy. But the point is the potential is there. And that's a conservative estimate. They have bounds, upper and lower bounds of what can conservatively be extracted. Again, if we put this into the same units that were used in the report, in 2005, the energy consumption in the U.S. was 100 exajoules. Geothermal energy is capable of sustaining over 100,000 times the U.S. energy needs. So solar and geothermal have huge capacity, and it's completely untapped at this point in time. Some communities around the world do use quite a bit of geothermal. In fact, the United States is the largest geothermal, generates the largest amount of energy by geothermal means in the world, but it's still a very small fraction of our overall energy use in the United States. So solar and geothermal are justifiably great targets for generating sustainable, renewable energy. The catch is the current technologies are not cost competitive with the inexpensive fossil fuels. So, and that seems to be the only driver that really works right now for most of society. If it's cheap, I'll use it. If it's not, if it's inconvenient, or if it's expensive, we don't shift our behaviors. We're not going to run out of fossil fuels anytime soon. And in fact, we're just going to extract more and more exotic, for lack of a better description, alternative fossil fuels. So we need drivers for change that work. And I would argue inexpensive renewables are great drivers for change. At the same time, though, we need to improve the efficiency of the use of our fossil fuels because that's 85% of the power generation in the world. So small improvements in efficiency can have dramatic impact on reducing the carbon emissions and improving our energy use around the world. Okay. So that's essentially what I'm trying to summarize here. You have the tools now to understand energy transfer. Of course, we're talking about really large-scale systems, but small-scale issues make a big difference, particularly when we have the population that we have. So you can improve the efficiency of the combustion of fossil fuels, alternative and renewables, and that's going to be an important role in our global energy future. And conservation efforts will also play an incredibly important role, and I can't stress this enough. These tend to be the not very exotic solutions, but they really do matter. It matters when you turn out the lights. It matters when you turn either the thermostat up or down. It matters when you carpool. Put on a sweater when it's cold out. Ride a bike to work. All of these energy savings matter. They all add up. And I would suggest that we work on all of those simultaneously. And I would encourage you to explore those energy transfer mechanisms using the tools that we've developed in this class. You have everything that you need for you to understand how much energy savings you can achieve through changing the thermostat setting in your house. You have everything you need to understand how much carpooling 1 day a week would impact your carbon emissions, would impact your energy savings, your oil offset, your gas offset. So